All right, so it's my great pleasure to introduce our last speaker, Alán Aspuru-Guzik. Now, Alán is really special. He's a force of nature and a big thinker. So you will see in what he will present that he's out there to conquer the world. And when it comes to AI, we do think big, and we'd like to really enable breakthroughs and not just, general artificial intelligence to make AI better and bigger and greater, but how can we impact people, right? And so Alán does have like a really interesting research agenda in terms of AI for science. And I strongly believe that with his leadership, we're going to see in the coming years some really important shifts, new paradigms that will emerge from this in terms of science. So in any case, Alán is a professor at the University of Toronto. He's also a Vector faculty member, C4AI chair, and also the director of the Acceleration Consortium. He's also editor-in-chief of the Royal Society of Chemistry, journal Digital Discovery, and also a fellow of the Royal Society of Canada. Now, his research interfaces of artificial intelligence, quantum information, machine learning, and chemistry. So without any further ado, please welcome Alán.
Well, I think we're in a great era right now because we have a confluence of many things happening together for science. What I'm showing you behind is all the amazing automation efforts that we have at the University of Toronto to build self-driving laboratories as part of Acceleration Consortium. So we have like these low-cost, high-throughput, AI-driven laboratories that like to accelerate scientific discovery. And this is one of the puzzle pieces that we need to actually accelerate science. We'll talk about another piece of the puzzle today, but I want you to keep in mind all of this accelerated experimentation that will allow us to then connect to something else, right? So we can even open doors. What is really cool about this is all computer vision enabled and AI planned. So let me see if my clicker works. Yeah, so today I want to tell you about our efforts on El Agente. El Agente is a very interesting project in the lab because we literally pivoted 80% of the laboratory to work on this. Like there's a moment where we said like, this is the biggest thing, let's just pull all our eggs in this basket. So I'm going to tell you a little bit about El Agente. So let's think about the problems that humanity has. We have political problems, environmental problems. Basically, I think the most important one for me is climate change, pollution, for example. And when you see a picture of this, like a little monkey in garbage, you might say, okay, yeah, there's garbage somewhere. Maybe I don't care too much about it, right? That's the problem with humans, that they don't really think in long-term horizons. So maybe you look at this stock photo of garbage, and then you say, okay, look, yeah, there's this guy in the garbage field, but he must be in another country. But turns out if you actually look at Toronto, Toronto has a huge garbage problem, okay, huge. There are some headlines I found this morning that says, Toronto is going to become one day a pile of garbage, and we really have to figure this out. So, for example, just simply recycling a material requires so much new science. One student in our lab, for example, is trying to figure out how to recycle polystyrene. And that itself is an entire PhD. So how can we accelerate things like recycling polystyrene or finding new battery materials with AI? So this is perhaps one of the biggest applications of AI that is non-controversial. Like the previous speaker was talking about generating silly videos. I have generated some silly videos myself. I think it's much more important to use all these data centers, infrastructure, and learning that we have from these systems to try to solve scientific problems to help humanity. So, but the real truth is that scientific discovery is bound by human bandwidth. Like, we are waiting for humans to do the next step, okay? So there's not unleashing of it in a way that actually we can discover science as quickly as, say, our models are moving, or even the robots I showed you before, right? So our goal with La Gente, which by the way is the agent in Spanish, is to accelerate scientific discovery for everybody. We want to have a democratization aspect, And we want to basically streamline scientific discovery. That doesn't mean the human leaves the role in scientific discovery. The human is empowered a little bit like the speaker from Thomson Reuters was saying, yeah, right? So the human is part of the loop, but is basically empowered by a series of, as you will see, many agentes and agentas, okay? So now I am in awe. I just ordered a Mac Mini to install my OpenClaw, literally. Like, we have a graduate student that has an OpenClaw. His name is Luis, and maybe he's in the audience, doing things for him and, debugging websites and things like that. So I'm fascinated by this technology. Obviously, I found this image on the internet of all the dangers of this technology. There are reports about OpenClaw basically extorting people and things like that. So like, there's a lot of safety issues when you actually unleash random agents on the internet. But as the previous speaker said before, the two speakers before said, we're in an era of agents, and so what are these agents and how can we use them for science? So I think what an agent needs to do in science, it needs to be able to generate hypotheses. Then, in our case, our agent will eventually, and we're starting to manipulate the robots that I just showed you, but due to safety reasons, it's much better to start first in the digital world, in the digital twin of the world. Like molecular simulations, material simulations, drug discovery, all of these things happen in a computer, they don't explode. So once we master the digital agents, then we can move on to the experimental agents. There's several companies that are trying to skip that step, and I already know from some academic cases, some laboratories that have exploded, literally, because they are being run by an AI and a human that was careless. So therefore, I think it's very important to actually first start in computing. And I mean, there is the hypothesis generation I will come at the end of the talk. A lot of compute and a lot of HPC interaction, and then, of course, the data analysis. And more or less, this is what happens in an AI for science project. So what I come to tell you here is that this is already happening. We have a tool called Agente that we want to release in the cloud for the public to use in a couple months, hopefully. The hardest thing is actually to have a scalable cloud platform that you can go and ask a question that is at the level of a PhD. 6 months ago, we had the level of a undergraduate student. Now we have PhD level type of questions that you can go to El Agente and ask a, like researcher at a major corporation type of chemistry question. And El Agente will go in and do, 25 hours of compute, hundreds of interactions with the tool, and come back to you. And then if you actually backtrack how much it will cost a company, like 2 weeks of work for an engineer compared to El Agente, which is basically clicking and waiting $25 worth of compute, including the LLM costs. So we'll come back to the $25 or so because, that's like an upper bound. Each one of our queries costs about $10. Just think about that. It's still a lot of money if you ask it 10,000 questions about 10,000 molecules, and you reason through all of them, right? Then it will cost you $10 per molecule, right? Which is about the same cost as experiment. Just think about how much electricity we're using, that it's about the same cost of maybe perhaps doing some chemical experiments in the real world. So this is work done by about 40 people for a year and a half. Here are them. This is the people that built El Agente. These are the real people that built El Agente. Some of them are here, so raise your hand if you have been involved in developing El Agente. I know Marcel is here, and Juma is here, and so anyway, there are some agentic people over here. You can talk to them. Professor Vanilla Bernales, which co-directs the Matter Lab with me, is there as well. And we're happy to answer questions after this if you want to talk about El Agente. So let me talk to you about El Agente that was published maybe now about 8 months ago. Okay, it's called El Agente Q, the quantum chemistry agent. This is the cover of the journal, and it's basically a street artist. We actually wanted to go against generative models, so we asked the street artist to generate the cover of El Agente. Okay, this is inspired by El Eternauta, if you guys know El Eternauta. So how do agents work? The story about agents is, in our case, we really want to think about the structure of a company or an institute, right? Like if you want to go to the Vector Institute, you don't want to actually, nobody will answer all the questions, right? You know that there's an HR person and there's like a event coordinator and there's a director, and all of them have a different role in the organization. So agentic systems for science, usually, not necessarily, but ours usually have several of them. For example, all the way to 60 of different sub-agents that have different specializations and different contexts of what they're supposed to do or other agents to call, okay? And this has to do with the limitations of large language models when they are actually looking at very large contexts. Sometimes a language model needs to look at the output file of a chemistry program and think about a bunch of other things, and like a human gets confused. So it's much better to create this delegation, and so therefore, really the secret behind these things is the semantic memory that is engineered to have these agents talk to each other. So this is kind of like the first GUI that we actually built for Agente. Is it working? Yeah. And what I like about this video, even if it's one of our OG videos, is you see there the agents talking to the sub-agents, talking to the sub-agents to execute the task. And in this case, it's a very simple demonstration. It's calculate the energy of the caffeine molecule. Raise your hand if you like caffeine. Good. Okay. You're still awake. That's good. Okay. But now, I mean, what was interesting about this one that we said, it's benchmarked on university exercises. Literally, we went to one of our colleagues in the chemistry department here at U of T, and we asked him for the the homeworks that he was giving his students in computational chemistry. And we made a level 1, level 2 type of benchmark where we were asking Agente to actually do these things. And, we're about, in the version number 1, 87%. Our second generation of Agentes are in the 98%, usually 95%, and so on, depending on the task. But now the tasks are PhD level, not undergrad. So the same thing that we saw in the previous speaker, improvement between VO2 and VO3, basically we're having the same kind of huge improvement in our agentic systems by the way that we are engineering them better, and of course the underlying models are also getting better at the same time. So this is non-linearity that is so exciting. So let's look at the question, right? This is a very abstract question in chemistry. Raise your hand if you know chemistry or some chemistry. That's good. Raise your hand if you liked chemistry in college. Okay, not very popular field, but anyway, you might remember a problem like this. It's actually abstracting what are cyclic molecules, right? These are like cyclic molecules that have some methane coming out of it. We write it in that way to the model, and the model actually just solves this problem, 100%, right? So it calculates the enthalpy and entropy of a particular series of reactions, compares them, and actually gives you some insight about the strain energies, right? So this is a question that you could have somebody spend a couple days in a computer building input files and calculating these quantum chemistry calculations to try to understand what happened. So the version 2 of this agent is called El Agente Contour. Contour is Quechua for condor, okay? And we like to call it condor because everything for us is now themed Latin American. We're tired of these North American themed things, okay? Like the same as Bad Bunny, right? So this is Contour, which basically means condor in Quechua, okay? And Juan is actually from Colombia, the first author, and therefore it's very fitting to call it El Agente Contour. So Contour is a little bit different than Q. So think about Contour as Q 2.0. And I like to put the names of all the authors on the left-hand side just to give you an idea of the magnitude of these projects. Each one of these projects is really like a big product at a startup, each one of them, okay? So in the left-hand side, you can see all the tools that the Agente can use. Orca and XTV are quantum chemistry packages. PySEF as well is another one. RDKit is a cheminformatics package. Architecture is a molecular builder, and so on, okay? We'll keep talking about tools. I believe that agents are as powerful as the tools they can touch. And there's a quadratic growth in the number of the power of the agent with the number of tools, okay, at least. So that means the one that controls the tools controls science, okay? So it's good to control these tools, and therefore you have to have agents that know how to use the tools best effectively and know how to verify that what the other agents did was correct. So there's a lot of back and forth here between our agents to make sure that what was done is correct. So now you can see there, a hierarchy. I'm not going to tell you a lot about all of it, but if you read it, at the top we have a computational chemist that is very ever knowing about the field, and then we have, in this particular one, is very interesting because we have more like field specialists, okay? And what is very nice about this one is that we enabled it with deep research. We basically told El Agente Contour, here are the manuals, go figure it out. So it has access to specific manuals for different software packages and reads the manual as it goes along, which is really great because instead of hard coding some of these rules in context files, now if the manual changes, the code will automatically change in a different way. Right? So that's the logo of Contour, and basically Contour has 100% coverage, or I think 90-something% coverage. I think there's one feature we don't cover, of the Orca package, okay? And I think we covered it, just haven't tested it, okay? So basically we can calculate a bunch of those properties here. I saw that nobody likes chemistry here, But think about any possible property of a molecule that you want to calculate. You can ask it to El Agente. And now, you might say that's boring, but we can ask El Agente very interesting questions. For example, what are the molecules related to the fact that when you open a book that is old, it smells like vanilla? Or you can ask it, why does benzene thiol never smell like alcohol? So questions about smell or about touch or about chemistry is everywhere. So if you really think about it, imagine that you were able to go to a language model of the ones that are out there in the internet and able to ask scientific questions that are interesting, like what will boil more than the other thing or whatever. So some of these things require a calculation, and we can actually get that calculation from very complicated high-performance computing. El Agente Contour is actually 60 sub-agents. And as I told you, some of them read the manual and come back and then go back and do something. And you can see here one of the action traces of El Agente Contour asking a PhD level question. It took about 25 hours of compute. And that's how a contour looks like. So now let's move on and let's think about the problem. I mean, the last talk was about how you look at video sequences, right? And you look at the video sequence and you kind of eventually start building a model of the world. I was fascinated by the previous speaker. I just had to go back to the back room, so I missed the last 10 minutes. But it was awesome. I was opening my mouth to see how amazing stuff is happening. Well, the same thing happens in chemistry here, but we're not even doing videos. We're doing static snapshots. So what we do is we combine the power of visual language models with the power of large language models. And we ask ourselves the question, can we build systems that actually edit molecules? And the way you want to think about molecular editors is that chemists change the molecules by hand in a graphical user interface. And that's what most of the computational chemists in the industry are doing. They're drawing these things in the GUI and then running them in an HPC system. So we built this structural editing agent where we built, Changhyuk actually built also a bunch of scripts that basically mimic everything that the person is doing on the GUI. Okay, so if in the GUI you can make a bond or break a bond or rotate an angle or change some conformation of a molecule, then we have a tool that you can in language do the same thing, right, with an API. And we also have a much more abstract way of doing it, which is just basically changing a little bit the way we render the molecule. For example, we enumerate the atoms, we put numbers on them, so the VLM has an easier way of tracking the atoms. And we asked a combination of those tools and the VLM, can you please edit this molecule? Okay? And what comes out of El Agente Estructural is amazing. Okay? So this is a question that blows my mind. Because this is a molecule that is like a coronin, okay? And then it's basically like a little concave thing, okay? And then you're asking it, can you place the atom on top of it or inside of it, right? Like it's either inside of the concave thing or on top of it, right? Or you can ask it to complex a cap, like if it was a sandwich, okay? Or put it in different hexagonal sides of this particular crown, okay? So you can see all the different pictures, all the prompts, and which tools the El Agente used to solve the problem. This is very high level for a chemist. And I am trying to plan a talk where I actually talk to El Agente. I couldn't do it for this talk, but where I come up to you and start talking to El Agente, and El Agente is doing these things, which will be amazing, okay? When we can do it interactively, amazing. So another thing that is super cool is that in a bunch of chemistry papers, we have these very abstract figures, like the one in the top left-hand corner, that describe some chemistry process in a very high-level abstract way. So in this case, there is a question about what potential two chemical pathways happen. This is a very common problem in chemistry. Does the reaction go this way or this way? Mechanistically, that means different rearrangement of the atoms, different ways that the atoms could rearrange themselves to carry out a chemical reaction. And we're asking El Agente to figure out, can you figure out which one of the two is? But for that, we need something that there's not much data in the literature for, almost zero, which is the transition state. That fleeting moment that goes between a particular reagent and a product. When you're in a reagent state, the atoms are in a particular configuration. In the product state, they are different. Maybe a bond was broken. What happens exactly in between is called the transition state. And we really don't have too much data on the internet for it. We have the brains of humans that can draw these transition states in the computer. But El Agente is able to build simple transition states. Now, there are some people here, like Andreas, which I think he was around. Where are you, Andreas? He's doing his entire PhD in trying to figure out how to find transition states with AI. Okay, so that's an example of a big problem, okay, still. But El Agente has some first steps into finding transition states using using these kind of tools. Now, remember I told you this was $25. Well, I mean, maybe $25 is great for if you live in the rich world, but like if you are in Mexico, you know, like, okay, $25 per calculation, right? I don't want to do that. So we started thinking about, is it possible to actually lower the cost and actually run calculations in GPUs and in parallel? And Jaru in the group has led a second generation of agents that is complementary to the first generation that can think using these VLMs and this large context, which actually uses a tool called Pydantic, primarily that tool, but many other tools, to actually build basically calculation graphs. It says, well, what I need to do is this, right? So I don't need to really reason between this step and this step. I just need to build like a strict dependency that if this finishes this way, I can continue. So it's basically a workflow builder that is very smart and inserts the LLM in the middle of the workflow to make decisions, okay? So that's why its Aztec-inspired logo there has this kind of weird workflow there, okay? And therefore, it has all these different tools. It can build molecules, calculate them in 2 dimensions and 3 dimensions, build molecular crystals. And some of the tools are kind of duplicated with other agents, and that's fine for us because we think about the agents as a network of agents that can talk to each other. So here you can see a very complicated plot, but that tells you about the routing and about all the different kind of steps that the El Agente Gráfico needs to do to actually move through different states of the calculation using a graph database and different actions that it needs to do on those states. Okay, so the database contains both the states and the actions and also allows the LLM to, in the middle, make decisions. And what is nice about this agent is that it offloads so much of the knowledge to that graph that it can be extremely shallow. You can have a single agent use this network. And Gráfico, for many of the benchmarks, is equally performing as El Agente Contour. In other benchmarks, Contour shines on because it's more flexible in some sense. Okay, but both of them are extremely good tools because you can imagine that once you have El Agente Gráfico or El Agente Contour generate a particular solution to a problem, you can extend it to a workflow, and the workflow obviously will not use the LLM, it will just use the HPC to solve the problem, okay? So this is an example, a slide that has an example of how to build something called metal-organic frameworks. Does anybody know what is a metal-organic framework? Actually, I know Mohammad Musabe is here, so he's an expert in that. They are like these molecular sponges that are used to soak CO2 out of the atmosphere, do filtration of water and all sorts of things. So think about it as a molecular sponge, and they're very beautiful to build, and he has an agentic system that can actually build them, and so our group in a different context. In this case, El Agente Gráfico is building this sponge. You can see it has a bunch of free air inside of it. This is the graphical user interface of Gráfico. It has actually has many different features than the original graphical user interface, but it gives you an idea of how an user is interacting with El Agente, still using her or his mouse to actually play around with this thing, but then go on typing a question and then going along and seeing what happens in the simulation. So this is the future of chemistry, just you're seeing it right now, okay? So now let's talk about something meta. Do we need to build every agent by hand all the time, or can we have an agent that builds agents? So like in the game Minecraft, that is a forging process where you forge different tools. Here we're also going to be forging agents. So we have an agente called Agente Forjador. This is led by Zijian Zhang and many other group members. So what El Agente Forjador does, it actually, instead of using the regular LLMs, it's using now coding agents, like Cloud Code, okay? And it tells Cloud Code, okay, I have this question, go and find the tools in the internet, and let's start building it. So it's a little bit more akin to how the language models for coding are used, okay? So in this framework, what we do with Forjador is basically we have a database of scientific questions. El Agente is tasked to go and find the right tools for them and grow a tool network that can be reutilized. So we have like 4 agents here at least, one of them that analyzes the tools, one that generates the tools, one evaluates the tool, and one that optimizes them. They have different contexts, they have different missions. The same thing, Cloud Code has different agents to do different things. So it's like an agent swarm type of approach. And each one of them actually can modify the code, which is really cool. All of them can actually go and tinker little scripts that run this thing, okay? So this is more about building a bunch of scripts to actually manipulate chemistry. So this is a plot that Zijian just vibe coded yesterday, showing you the growth of El Agente. As you're asking it more and more questions, El Agente Forjador is going to the internet and downloading more tools and building agents for them. So this is perhaps a little bit more uncontrolled than the previous agents, but in many benchmarks it does as well as them. And you can see there some of the tools that now, if you ever wanted to do it again, you could do, like quantum disorder generator. So now you have a tool to do quantum disorder, or to do, Hubbard observables or something like that. This is actually doing some quantum computing stuff. You can actually see this quantum computing stuff. This is a very interesting problem in quantum control that we chemists like a lot. It's called stirrup. It's how can you transfer one quantum state to another quantum state through an intermediate state? It's a quantum control problem that our Agente Quantico that we built by hand and reads the manuals is a little bit similar to Contour. Found a solution that only oscillates once. That's fine. But then Forjador, in a one shot, found a solution that oscillates a few times but gets to the same objective. Okay? So that's fantastic. So now, El Agente está presente. What do I mean by that? There's many, many, many other agents that we're building. So I just showed you the tip of the iceberg. We have all these people in the group building agents. The famous story is El Agente Quantico, which I have no slide for. I don't have space. But I'll tell you that Nacho, the first author of this agent, came to the group in around October. And then by December, he had an agent paper. So this is also accelerating the career of our postdocs, okay? Which is great because postdocs is like this weird limbo between a PhD and a job that pays well. And Nacho is accelerating his time in limbo, okay? By writing papers about El Agente. So Marcel, who is here as well, I think, is the main author of El Agente Fármaco, which is our drug discovery agent. El Agente Teórico is our theoretical chemistry and physics agent to actually do manipulation of equations. It uses SymPy as a tool in the backend. And El Agente Seguro, Barini has been co-leading all of these projects, but one of them that she is particularly pushing forward, is El Agente Seguro, which is our chemical safety agent, right? So that's an idea that I think is so important. We need to have chemical safety before we enter the lab. But sorry, we also have a solid-state simulation agent that is posted on the archive today at 3:30. We have an agent that is going to be called, this is being built. That one is the one that's kind of, we have parts of it everywhere, which is going to be a feature of how our agents talk to each other. Like Mark Carney that goes around the world and like makes deals with like 50 countries at once. So this agent is going to be like a Mark Carney that goes around and makes deals all over the world. And is going to be able to take one agent and talk to another agent, to talk to another agent, including, and that's why it's called the Diplomatico, everybody else's agent on the internet that does science. That's our main ambition. That if there's some open source random agent that somebody built in China, we take it and put it in our Agente network. So El Agente network will soon become not only our agents, but everybody else's agents in the world. So that's Diplomatico. And then we're also, CGen is also building Agente Creativo, okay, which is our creative thought agent, brainstorms and comes up with ideas and hypotheses. And that's perhaps the scariest agent of them all, right? Because it becomes very smart. So here are some snapshots. Actually, I didn't even put there Potente, but Potente is our chemical potentials simulator for classical potentials. That's a battery, by the way. So we just can have a prompt and simulate the dynamics of a battery. Just by saying, oh, please simulate the dynamics of a battery. And you can see the beautiful atoms moving around. And that's called Agente Potente. This is Marcel's Fármaco. There's a very, very powerful tool called Bolts. And this tool is actually used to simulate the drug binding efficacy of compounds. And many, many people are very excited about Bolts because it actually goes beyond AlphaFold and actually allows people to go directly and screen some compounds. Our lab just had some results for some compounds that we were able to screen with Bolts and verify experimentally. So Bolts is really a game changer. And something that was a real game changer and a true story, my talk is almost ending, but I'll tell you the story. Our NVIDIA colleagues came to visit the lab. And during lunch, during the morning, they explained to us how this NIM, basically the web services of all the NVIDIA drug discovery software worked. And then we tell the students, you have a week to build a pharma drug discovery agent. So they went back to a room, they did a hackathon, and by the time the NVIDIA guys were leaving for the evening, for dinner with us, they already had a prototype of the Agente Fármaco. So this is Fármaco, of course, much more advanced, but this Fármaco, they're doing real drug discovery tasks. You can see all the files that it touches, all the complicated setups that are now automated. And a true story is that when I started my research group back then at Harvard, one of the first things I wanted to know is how the Lindblad master equation worked. So a postdoc that came from Toronto, actually, from the physics department in Toronto, showed me how the quantum master equation worked. First time I learned about open systems, and he was going back and forth. It was 3 blackboards, and I still have the photo of those blackboards somewhere. So I have to go dig in my history to have it. So Nacho, which is leading the Agente theoretical team, which by the way has all Latin American authors so far, which is really cool, basically derived the Lindblad equation using SymPy and created this latex with colorful boxes and so on. Much better than the blackboard that I started back in 2006 when I started my research group. And if you notice at the end, it actually carried out a simulation with Agente Cuántico. So it not only does the theoretical simulations, the theoretical calculations, it can, on the fly, build a model and calculate it. So that's El Agente Teórico coming up in the future. So, as you can see, we have a very bright future. We have chemistry, structural editing, forging, lab safety. I told you about most of these agents. They're coming out in a very, 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 very rapid progress. We really need help from people that can help us stand up the platform. We do have a web platform. I showed you one of the screenshots of it. The Agente Fármaco was in the web. That video I showed you is a cloud version of El Agente, but still not ready to give it to all of you at once. It will crash our servers. It will crash everything, right? So we're working on that. And with that, I'm just going to thank the research group that built it all. This is a Matter Lab. Many of the people that I mentioned are in that picture as well, or photoshopped into it in the back, some of them. And I want to end with this quote that I really like, okay? This is a quote by Borges, because I want to preempt your first question. What is the role of the scientist? Well, the role of the scientist is this one, right? This is Borges talking about chess. It's a chess player, right? And he says, which is the god behind the god that moves the player, that moves the piece, that starts this game of dust and agonies. I think it's fitting because we started with Chris Madison talking about AlphaGo, which is not dissimilar to chess, right? So here are our agents solving some science problems. What is the role of the scientist? Well, build these agents, interact with these agents. And with that, I literally ran out of time right now, so I'm happy to answer any questions. Thank you.
All right, thank you, Alan. So any questions? Okay, so perhaps while people are still thinking about questions, let me ask you a question. So
yes,
you gave a very inspirational talk. I mean, this is amazing, but obviously there must have been some challenges. You must be aware of some limits and some failures. Can you tell us maybe what are some of the things that are maybe holding us back to, keep advancing this?
Yes. So it's quite funny how the challenges that we have are intrinsic challenges in chemistry. For example, the conversion of a string, which is called a Miles string, usually that's the format, into a 3-dimensional molecule has all sorts of pitfalls that chemists run with computationally all the time. So that's why we built El Agente Estructural, to try to go around them with sophisticated reasoning. So what is funny is that I think most of the pitfalls that we find are the ones that already exist in natural computational chemistry. It's not pitfalls for the agentic approach per se, but pitfalls of the field. And therefore, we're moving to the step where we build agents to solve those pitfalls. Now, in the agentic side, yeah, there are ones. For example, when we build a web platform, sometimes there's timeouts. There's a bunch of bugs that, like developing something like a web platform happen. So behind the scenes, things crash. You have to rewrite the code. And once an agente is ready, well, as we say in science, it doesn't work. When it works, you publish a paper and it doesn't work again. That's basically how we do these agents, right? But what is very nice about them is once the agents are ready, we move on to the next one and the next one, and eventually they will all talk to each other. And things are moving really rapidly in the group. So I think the challenges are the challenges you will expect by developing an AI system like anybody else. Like, the bugs in your actual DevOps or bugs in the code. But other than that, I think we're all having fun. Yeah.
Great. Okay, I see some people here at the microphone. Please go ahead.
Hi, Alán. Great talk. And I just wanted to ask, so in your agentic workflows, it seems like you often, or a lot of these projects rely on an LLM's ability to make decisions about materials design or simulation. Do you have any vision for leveraging the scientific literature to make even more informed decisions in your agent?
Yes, so I forgot to tell you that, but yes, we do have agents. A lot of these agents, you can drop them a paper and say, follow this paper, or look at these 5 papers and see what's up, right? Like we have ability to do those kinds of things. But the Agente Creativo, the one that we haven't told you too much about, it does a lot of that, goes to the literature, makes hypotheses, compares them to each other. And there are very interesting places like Future House or this company called Edison, where they're trying to build this type of reasoning agents. So yes, we also have that capability. Many times we call third-party research, deep research engines, and then what comes out of them informs our agents and interact with each other. So yes, we can also do that kind of work. I focused more on the tool use here because what I find lacking in those type of people is that they do all that work, but then their agent cannot do anything. It's almost like hypothesizes something and I cannot do it. We are the opposite. We want our agents to be able to do everything, and then the reasoning will come out as cream on the top.
Yeah, that makes sense. Thanks.
Yeah.
Hi, Professor. I really enjoyed your talk. Thank you so
Thank
much
you.
for sharing. My question was related to the idea of reproducibility and this idea of control within science. I come from a biology background, and I think that it's well established that reproducibility of results published in papers is often hard to achieve.
Correct.
And it's a huge crisis. So I guess my question to you is, within the agentic workflows that Agente, sorry, I'm horrible at pronouncing that, what types of steps are being taken to address that? And I guess within like the DAGs that are being produced, are there considerations being made that if one assumption is being missed, we try something else or stuff like that?
Yes, and yes. The first thing is, one of the main reasons we like to build self-driving labs, which is the video I showed at the beginning, is because in many cases, a self-driving lab is much more reproducible than a human. Because the human might be just doing an experiment and gets distracted and drops more chemical. And the experiment is a little bit different. The same thing happens in biology. And therefore, first of all, with robotics and automation, we lower that problem a little bit. And also, we have everything digitized. Okay? That's a big thing also for El Agente. One thing that is very important is people don't have good logs of what they did, okay, obviously. And with this case in El Agente, you have like extremely detailed traces of everything that happened. So you can go back and debug if there was something wrong. And finally, yes, we are putting as many check marks as possible or as many decision points to make sure things are kosher. Usually what happens when El Agente fails a benchmark is because it missed some numbers in the output, and we have to reprompt it. So there's many times that I think Chris Madison was just saying this, and I agree with him. It's like LLMs are kind of like stochastic retrieval from databases. So sometimes you ask it a question, doesn't do it. So you have to ask it again, right? Like a stubborn person. It's like, wait, you forgot this. Okay, I forgot this. So we have systems that allow us to do this, but one of the most important things about El Agente is all our published agentes have a benchmark. And on those benchmark problems, we do it 10 times, which is a lot of money sometimes. Like last month, we spent $30,000 worth of LLMs in the group to actually verify all our models to make sure they're actually published with benchmarks, which unfortunately in the AI for science literature, almost no group in the world does that. And it's pretty annoying that you see these papers with 3 case studies, but you never know when their model failed, as you say. So how do you know if this is not bullshit? So we like to make sure that all our agents are actually benchmarked, so people actually can see that what we're doing stands the test of time and our reputation is preserved.
Appreciate it. Thank you.
Great. One last question.
Yeah, thank you. It's a wonderful vision, and it's the wild west of growing agents.
Yes.
I'm just curious what your thoughts on, and are you already looking into the security and attack vectors with this?
Oof.
Do you have sheriff agents that you're going to hopefully deploy? If you go out there and you just take a manual off the shelf, prompt injections are just ripe for the taking with it. So how are you envisioning sort of locking things down when that's a potential?
We're so scared about that. That's the reason why the other chemists keep telling me, Alán, why don't you release the code of El Agente? The first thing is like, we don't have time to think about all of those implications. At the moment, let's learn how to do these things and then release something prudently, number one. No code. El Agente, sorry guys, we're not going to give you the code of El Agente, mainly for that reason. But then the other aspect that we think a lot is learning from things like OpenClaw, how people have been able to make these OpenClaw type systems more and more encaged. Right, so I think learning from what the community has been doing and try to make their agents safe, In our cloud instance, what we do is we spawn an instance and then run our agentic stuff and delete it. So like, if you hack, you just hack that thing that we spawned for that moment. It's probably still very insecure, but it's not like we have a central system that everybody's using, and then if you hack it, you hack everything. So we're not security experts. We're chemists and physicists and computer scientists that we're doing our best. But I think that's one of the things that keeps me up at night, that somebody uses El Agente to steal somebody else's email or something.
Well, I'd be curious to see when you build that red team to start stress testing your systems.
Very happy to collaborate with people that want to do that. This is the reason why we don't want to connect them to a chemical robot first. So we don't want to explode a laboratory, unlike some of our colleagues that are connecting LLMs to robots already. And we think that's not actually that prudent. The same thing here is like releasing the code to the internet should be prudent so that we don't create damage that we were not intending to create.
Thank you.
Great. All right. So this concludes our last talk. So big round of applause again for Alán.
Thank you.